In this video we're going to look at how equations can be solved using the methods of 3x3 matrices that we introduced in the previous video. If we have a system of equations with three unknowns and three equations of the form ax plus by plus cz equals p, dx plus ey plus fz equals q, and gx plus hy plus iz equals r, then that system of equations can be written as a matrix equation of the 3x3 matrix ABC, D, E, F, G, H, I times by the column vector x, y, z equals the column vector P, Q, R. If we write M as being the 3x3 matrix ABC, D, E, F, G, H, I, then what we've got is we've got M times x, y, z must equal P, Q, R. If the matrix M has an inverse, M inverse, then we can multiply each side of the equation by M inverse to obtain M inverse times M times x, y, z equals M inverse times PQR. But M inverse times M is the identity matrix. So we've got the identity times by x, y, z equals M inverse times PQR. And the identity times x, y, z just gives me x, y, z. So we've got x, y, z must equal M inverse times by PQR. And in that case, the equation has a unique solution. So if M has an inverse M inverse, then the equation has a unique solution. So let's look at an example of this straight away. Find the inverse of the matrix A, which is 2, 1, 1, 0, 1, 2, 2, 0, 1, and hence solve the equations 2x plus y plus z equals 8, y plus 2z equals minus 4, and 2x plus z equals 4. Well, the first part of this question we actually did in the previous video, where we discovered that A inverse is 1/4 of 1 minus 1, 1, 4, 0, minus 4, minus 2, 2, 2. So, the system of equations that we've got, 2x plus y plus z equals 8, 0x plus y plus 2z equals minus 4, 2x plus 0y plus z equals 4, can be written in matrix form as 2, 1, 1, 0, 1, 2, 2, 0, 1 times by x, y, z equals 8 minus 4, 4. In other words, in matrix form, we've got our matrix A times by x, y, z equals 8 minus 4, 4. If we pre-multiply each side by A inverse, then we've got A inverse times by A times by x, y, z equals A inverse times 8 minus 4, 4. A inverse times A is just the identity matrix. So we've got the identity matrix times by x, y, z is A inverse times 8 minus 4, 4. The identity matrix times by x, y, z is just x, y, z. So we've got x, y, z equals A inverse times by 8 minus 4, 4. We know that the format of A inverse, it's 1/4 of the matrix 1 minus 1, 1, 4, 0, minus 4, minus 2, 2, and we've got to multiply that by 8 minus 4, 4. And if we do the multiplication, and you can check that this is correct for yourselves, we get x, y, z is equal to 4, 4 minus 4. So the solution of the simultaneous equations is x equals 4, y equals 4, and z equals minus 4. Now, it should be noted that this method for solving simultaneous equations will only work if the matrix A has got an inverse. So, the inverse matrix method for solving simultaneous equations only works for systems of equations which have an inverse. In other words, for systems of equations whose matrix has a determinant which is not equal to naught, or for systems of equations whose matrix is non-singular. What's more, the whole process of working out the inverse of a matrix requires a huge number of arithmetic calculations. Now, if we consider the system of equations 2x plus y minus 3z equals 0, x plus y plus z equals 3, and 5x plus 3y minus 5z equals 3, or it's a matrix equivalent, which is 2, 1 minus 3, 1, 1, 1, 5, 3 minus 5 times by x, y, z equals 0, 3, 3. Then, the first thing is you can calculate the value of the determinant. I'd like you to check this yourselves, but that comes out to equal 0. So that means that the matrix is singular, so that there is no inverse matrix. So the method that we've used in example 1 won't work. However, if we look at the equations, you may be able to spot the fact that if you have x equals 1, y equals 1, and z equals 1, then that system of equations is satisfied by those values. So what this is telling us basically is that the inverse matrix method for solving simultaneous equations won't deal with all systems of equations that we might meet. And in the next video we'll see an alternative and rather more efficient way of solving simultaneous equations in 3 unknowns. So again, now to have a look at a second example where we have the matrix M is defined by the matrix 1, 1a, minus 1, 1, minus 10, 1, 0, 4. We're told that the matrix is a determinant of minus 4, and the first thing we have to do is find the value of A. So the determinant of M, then we need to write out the matrix and then repeat the first 2 rows underneath. And then using our diagonals, well, going down the top left to bottom right diagonals, the first one we've got is 1 times 1 times 4, which is 4. The second one is minus 1 times 0 times A, which gives me 0. And the final one is 1 times 1 times minus 10, which gives me minus 10. Going down the other diagonals from top right to bottom left, we've got A times 1 times 1, which gives me A. We've got minus 10 times 0 times 1, which gives me 0. And we've got 4 times 1 times minus 1, which gives me minus 4. So, the value of the determinant is going to be 4 plus 0 plus minus 10. Take away the result of adding up the A plus 0, take away 4. So, tidying that up, I've got minus 2 minus A, and that has got to equal minus 4 because we've been told that the value of the determinant is minus 4. So we've got the determinant of M is minus 4, means that A has got to equal 2. Now for part 2 of the question, or part B of the question, we've got a matrix N is defined by minus 1, 1b, 1.5, minus 0.5, c, 0.25, minus 0.25, minus 0.5. Show that for suitable values of b and c, which should be stated that n is the inverse of m. Well, if n is the inverse of m, then we must have m times n equals the identity. So, let's have a look what happens when we actually work out m times n. The top left entry is 1 times minus 1 plus 1 times 1.5 plus 2 times 0.25, which gives me 1. The entry underneath is going to be minus 1 times minus 1 plus 1 times 1.5, take away 10 times 0.25, which gives me 0. And the bottom entry in the first column is going to be 1 times minus 1 plus 0 times 1.5 plus 4 times 0.25, which gives me 0 again. Moving into the middle column, the top entry is going to be 1 times 1 plus 1 times minus 0.5 plus 2 times minus 0.25, which gives me 0. The middle entry is going to be minus 1 times 1 plus 1 times minus 0.5 plus minus 10 times minus 2.5 minus 0.25, and that gives me 1. And the bottom entry is going to be 1 times 1 plus 0 times minus 0.5 plus 4 times minus 0.25, which gives me 0. And for the final column, the top entry is going to be 1 times b plus 1 times c plus 2 times minus a half. In other words, I've got b plus c minus 1. The middle entry is going to be minus 1 times b plus 1 times c plus minus 10 times minus 0.5. So that's minus b plus c plus 5. And then the final entry is going to be 1 times b plus 0 times c plus 4 times minus 0.5, which is going to be b minus 2. Now, if n is the inverse of m, then m times n must equal 1, 0, 0, 0, 1, 0, 0, 0, 1, which will be the case if b plus c minus 1 is 0, minus b plus c plus 5 is 0, and b minus 2 equals 1. Well, if I have b minus 2 equals 1, that certainly gives me b equals 3. b plus c minus 1 must equal 0, would tell me that c had to be minus 2. And if we check on the middle equation, minus b plus c is going to be minus 3 plus minus 2 plus the 5 actually equals 0. So all three of those equations will work if I have b equals 3 and c equals minus 2. So n is the inverse of m, provided b is 3 and c is minus 2. Moving on to the final part of the question, we've got to determine the 3 by 3 matrix X, which satisfies the equation X times by M equals 4, 0, minus 8, 4, 4, 12, minus 4, 8, 16. If we look at the structure of this equation, what we have is an equation of the form X times M equals a matrix A. If I now post multiply, that is multiply on the right hand side of each part of the equation by the inverse of m, that is n, I've got x times by m inverse equals a times by m inverse. We know that m times m inverse is the identity, so I've got x times the identity must equal a times m inverse. In other words, I've got x is a times by m inverse. And m inverse is our matrix N. So I know the solution of this equation is given by x equals a, that was the matrix 4, 0, minus 8, 4, 4, 12, minus 4, 8, 16, times by the matrix N, which is minus 1, 1, 3, 1.5, minus 0.5, minus 2, 0.25, minus 0.25, minus 0.5. And all that remains to be done now is to carry out that matrix multiplication, which turns out to give us x equals minus 6, 6, 16, 5, minus 1, minus 2, 20, minus 12, minus 36. So we've seen a couple of ways in which we can use 3 by 3 matrices to solve equations.